Hello, class. We're starting chapter 5 now of the recorded lectures. This would be section 5.1. And chapter 5 and chapter 6 are the two kind of springboards and foundations for those of you heading to trigonometry and calculus. And if you haven't had a high-level algebra class before, a lot of these concepts are going to be new. And so chapter 5 talks about higher order, what we call polynomials. So the polynomials that we all know and love now are the linear equation and the quadratic equation. And now we're going to talk about equations that have x cubes in it, x to the fourth in it, etc. And how do we analyze those? And how do we figure out how these equations behave, how to sketch the graphs, and find the most important points to be able to analyze the equation. And so we're going to walk through all that, and including we're going to sneak in something called rational functions, which talks about functions that are fractions, where the x is in the denominator. So section 5.1 has a lot of important concepts. So this will probably be split up into several small lectures. So the first thing we want to do is to introduce this concept of a polynomial function. Sorry about that. I'm trying to click the right button. There we go. So here is our definition of a polynomial function. And it's like, look at all this. Well, these ideas are really important. So if you're given this equation, A are all real numbers, and then you have the variables x, and n are positive integers. So they would be the numbers 1, 2, 3, 4, 5, etc., etc. And so the idea is that these are polynomials. And so these would be equations that would look like this. F of x equals 3x cubed plus 6x plus 5. It would look like g of x equals 7x to the fifth plus 7x plus 8. And so it won't look like this. H of x equals, say, x to the 1/2 power plus 6. Because 1/2 is not an integer, right? A positive integer. And so this is not a polynomial. So in this section, we're not going to be dealing with this. Also, let's see. Let's just call it c of x, a cost function. We won't see an equation that looks like this, x to the -2 power plus 6. Because again, this is a negative integer, right? Not a positive integer. And this has to be a positive integer. Okay, so ideas. So say like we had this equation here. Let's call it 6x to the third plus 5x squared plus 4x plus 3. So let me give you a couple more definitions. The degree of the polynomial is the highest exponent of x. And again, we call this n, and that would be this number 3 here. So hopefully some of these will be easy to identify. And then there's this idea of the leading term. And we will use that in something called the end behavior test, which we'll talk about shortly. And the leading term is the one with the highest exponent, and that is 6x cubed. Sometimes we talk about leading coefficient, and that would be the number 6. So whatever's in front of the highest exponent. Most of the time, we really focus on the whole leading term. And then we do know one other thing, right? What is the y-intercept of this equation? Well, remember, it's when x equals 0. And so when you plug 0 in, the 6x cubed goes away, the 5x squared goes away, and the 4x goes away. And so this is x equals 0, y equals 3. Whoops. So that's this guy right here. So the y-intercept's usually really easy to get. We're going to talk about how to calculate the x-intercepts in the next couple weeks throughout this chapter. This is much more challenging. And so our ultimate goal when we get to the last section of chapter 5 is to show you all these kind of cool techniques and some new theorems and ideas to make these calculations. So hopefully so far so good. Let me clear this and get back to some more definitions. So this is a really important concept about the graphs of any polynomial. So the graphs of any polynomial are continuous and smooth. So there's no jumps, there's no holes, there's no sharp corners. So very well-behaved graph. The other thing that I hope you realize is that when you look at these equations, the one thing that is the domain of these equations is all real numbers. Because if you plug in any value of x, right, there's no square root, there's no dividing by x, so don't have to worry about divided by 0 or square root of negative numbers. And so the domain are all real numbers. Depending on the type of polynomial, sometimes the range is restricted, like we talked about, for example, in quadratics. So just to show you, and again, we did all this already, but this is kind of a nice overview. Here's a quadratic of x squared minus 2x minus 3. And you could see the graph, you could see the vertex, you could see the domain, you could see the range. I think we beat this up enough in chapter 4. But here's what we're going to learn to do is to start sketching these guys here. And so here's a cubic. And a cubic is, I would consider, an order of magnitude harder to deal with than a quadratic. We don't have any cool quadratic formula to deal with to be able to find, for example, the x-intercepts. So find the x-intercepts of a cubic, in my opinion, is 10 times harder than in a quadratic. So we'll show you these techniques as we move forward. But let me point out a couple things on the graph. So point out, number 1, that if you look at this equation, x cubed plus 2x squared minus 11x minus 12, our y-intercept is minus 12. And you can see that this graph passes through 0, minus 12. Very important. That's the easy calculation. You can see that I've shown you here, and I believe it's in the book as well, how you would factor that. And we're going to show you techniques to get to that point, but now I'm just giving you the factorization. So what does this mean? Well, when you set g of x equal to 0, these are the 3 x-intercepts. Minus 4, minus 1, plus 3. And you can see that's where we have these. So what we do in college algebra is to show you the y-intercept, show you how to calculate the x-intercepts. The one numbers that you won't be able to calculate until you get the calculus is where these two, well, remember we call those relative maxes and mins. You know how many there are, but you don't know where they are until you get the calculus. So when you get the calculus, you'll learn how to calculate these 2 points. But the other thing that we're going to learn here is to find out what are the maximum number of turning points, is where we're going to define them as. And also in algebra, you know what happens when x goes to positive infinity. Does this graph go up or down? And if x goes to minus infinity, does y go to plus or minus infinity? And that's called the end behavior or leading term test that we will talk about in this section. So here are some examples of polynomial graphs. Here is quadratic. Here is a horizontal line, which probably is the simplest one. You can see here is a cubic, x to the third. So the degree of this polynomial would be 3. And the leading term is 2x cubed. Here's a x to the fourth one. And you can see it starts to even look a little bit funkier. And so you can see that the y-intercept in this case is 0. So when the y-intercept is 0, that means it occurs at the origin, 0, 0. So that's the one time where the y and the x-intercepts are both the same point. You could have multiple x-intercepts, but remember, in a function, because of the vertical line test, you can only have one y-intercept. Here's an example of some other graphs that are not functions. Here's the absolute value, and you can see it has a sharp corner, so that's not polynomial. You can see this is not a polynomial because it's a fractional exponent. Here's a square root, so definitely not a polynomial. And we're going to talk about this in a little bit, but this is called the rational function. And you can see that the x value is in the denominator, and the graph, as you see here, is definitely not continuous, right? Big space in between those two lines. So that's the first part of section 5.1. And so the next recorded lecture, we'll talk about the end behavior, or some books call it leading term test, on how to find on the graphs what happens when x gets really big in the positive direction and when x gets really big in the negative direction.